All right, what's going on, guys? Good evening, everyone. We have a very important lesson today. We have gone through several distributions. We have dealt with Bernoulli, we've dealt with binomial. We also talked about Poisson distribution, and we talked about geometric distribution. Then we went on to a continuous distribution, which we had a whole lot of time on normal distribution, and I'm sure you guys really was able to comprehend what we were saying. We talked about standardization. We talked about the use of the Z table, right? But there's something we want to do today, a very vital aspect of distributions, and just like I told you guys before, we have situations where we have to make use of some other distribution in solving questions on another distribution. For instance, we have dealt with a situation where, as I told you guys, you had a binomial distribution, but instead of us going on to make use of binomial, we'll be making use of Poisson. All right. Now, in such situation, I told you guys that when you notice that we have a small probability with a large number of trials, that's a very suitable situation for making use of Poisson distribution. Now, there's another scenario where you would be seeing a question and it will be it would look very much like a binomial. It will actually be a binomial distribution, but it won't be very ideal to make use of a binomial distribution. And I will be telling you the reason very soon. We have a situation like, for instance, let me give you an example. If we have number of trial to be 100, and we are told to find the probability that x, a random variable, is greater than or equals to 45. Now, if you look at this question, you would see that it's very possible to solve using binomial, but it's not very ideal because if you're going to follow the binomial approach here, that means you will have to find the probability of x when it was equals to 45, because we said greater than or equals to 45, or when it was equals to 46, equals to 47, up until you got to 100. Now, can you visualize how tedious that would be, you having to solve 45, 46 up until 100? This is a very vital moment where, rather than going on with your binomial approach, you could make use of normal distribution in solving it. It's a very solvable question, albeit it's not very solvable. It's going to be very tedious using a binomial distribution, majorly because of the large calculations you would have to go through. And that's the reason why we have to understand the way to make use of the normal approximation in solving a binomial distribution. All right. Now, it's a very simple technique, although you have to understand how to make use of it. So I'll be moving more into the way to go about it rather than saying so much on the introductions around it, because I would just love you to be very aware of the fact that these questions are very examinable. I believe I've seen it in about probably 2 different past questions where you would see a question where it looks so much like you want to make use of the binomial distribution, but if you attempt to use binomial distribution, you will probably not solve any other question and probably not even be done with it till your exam is done. And you would see in that kind of scenario, you're not expected to make use of a binomial distribution. All right. Now, look at I will just give you about 6 different steps. Very, very simple. Very, very simple step. You saw it's not, everyone can run through it. It's not difficult at all. Now, the very first step, I'll give you about probably 4 steps majorly for you to run through, for you to make use of the normal distribution. The first one is you have to check if this is suitable for normal distribution. You have to check if you should make use of normal distribution in this case. All right. The first thing is for you to check. Now, how do you check? That's the question to ask. How do you check if this is viable? If the question you have at hand is viable for a normal distribution? Well, very simple. You go on to find the mean multiplied by the probability, and also the mean multiplied, the probability for success here, then also the mean multiplied by the probability of failure, which I believe we all know all these things. So when you multiply the mean by success and you multiply the mean by failure, the answer you get should be greater than or equals to 5. Now, I want you to know that different textbooks make use of different checking criteria. There are some textbooks that would say the multiplication of the mean and the probability of success and the multiplication of the mean and probability of failure should be greater than or equals to 10. Some people will move more on that, but we will be using more of greater than or equals to 5. So this is the check. So once you notice that the multiplication of the mean, of course, I believe we all know how to find the mean of a binomial distribution. It's something you guys can always recollect because we said the mean for a binomial is n multiplied by p. And we also said the variance, if you recollect, is npq. That's n multiplied by p multiplied by q. Now, when you do this, you will find your mean, multiply it with the probability of success. If the answer you got is greater than or equals to 5, of course, and you do the same for this other side, then that means this is very much ideal to solve using the normal distribution. So that's the very first step. Now, the second step, which of course, this is just in order to put it step by step, is for you to find your mean, which I believe you have found already in this case, of find your mean and your standard deviation. That's step number 2. Find your mean and standard deviation. All right. Number 3 is for you to write in probability notation. All these things are just, again, it's very, very cheap and easy to understand. Write in probability notation, and what that means is that you want to put it in probability notation. The meaning of this is that there are some questions where it will be a word problem and you would not be given it in this form. This form you have here, you will not have it like that all the time. So in the case where you were not given this, what you want to go on to do is to write it like this. This is what we mean writing in probability notation, where you want to bring it out this way. And you using hex, you'll be using x. Of course, we majorly use x as our random variable. So just like this, probability of x greater than or equals to 45. In another case, maybe probability of x less than 22. Maybe probability of x equals to 20. So whatever the case, whatever the question was saying, you want to write using probability notation using x. So you do that, and the next thing, which is the most important thing of all these things we're talking about here, the next thing you want to do, which is the most important, is that you want to go on to use what we call continuity correction. Now, this is continuity correction. This is where I'm going to spend a little bit of time to explain, because you want to make use of continuity correction. This is very vital for you to get the right result. So just a quick recap, you want to understand how to solve binomial distribution using normal distribution. It's a very important aspect of probability distribution function, where you're given a question. It's a binomial question, and in some cases, it's not even feasible using the binomial. When I say not feasible, I don't mean it's not solvable using binomial. Like if you notice your binomial table, which I believe every one of you have that already, the binomial table in many cases will only give you values of n up until 20. And when it gets to 20, you will see it probably gets to 25. And if you're lucky, you see the table for 30. So you don't tend to see binomial tables that has 21, 22, 23. So you see why in the case where they're asking you to find the probability of x greater than or equals to 22. Now, if you want to make use of the table to solve this question, which is still, the most tedious one is using your hand. Of course, the table is much more easier than using your hand. And then this one I want to explain now is the easiest. So if you have a question like this, of course, it's going to be very difficult because you'll be looking for your table for 22, 23. Even let's say if the n values was still 30, of course, you'll be looking for 22 up until 30. Or even let's say it was even 25. That's still small. So 22 to 30, obviously, you want to just have 22, 23, 24, and 25. Sorry, 22 to 25. Now, you can use your hand to solve this, obviously. But if you want to use your table, you would not be able to see, you hardly will see a table that mirrors n equals to 22 or n equals to 23. Most of the time, you will see 20, you'll see 25, probably you see 30. So that's the reason why you want to know this procedure, how to make use of normal distribution. It's very simple. Once you understand the procedure, you don't have issues at all. So let's get right into it, and we'll start by solving a question immediately. And you need to really focus so you can get the best. So we look at this question, and the question says, let x be a binomial random variable. So let x be a binomial random variable with the sample size, the number of trials n being equals to 75, and the probability of success p is equals to 0.6. So the question which I want us to solve now is, what is the probability of x greater than or equals to 52? Now, if you look at this question, you can see how very precise it is. It looks very simple. If you know binomial, you would want to make an attempt to solve this using binomial. But the issue with that is that if you look at this, what the question said is for you to find the random variable being greater than or equals to 52. And don't forget your number of trial is 75. Now, for you to solve this, if you're going to use your binomial, you'll be having to do when x was 52, because it was equal to 52, when x was 53, 54, 55, up until you got to the value for n, which is 75. Now, can you picture yourself in an exam hall having to solve this? And how long is it going to take you? Of course, if you recollect the formula for your binomial, your probability function, mass function, we have it as this. So, of course, for each of them, if you are going to use this binomial, you want to say 75 combination 52, then probability of success, which was given as 0.6, raised to power, in this case, 52, then 1 minus p, that's 1 minus 0.6 raised to power 75 minus 52. So you want to solve for this, and Of course, when you're done solving this, you'll be adding the values with that of 53. You do for 53, do for 54, up until you go to 75. So that's the process you will have to run through if you had to use binomial. But you don't have to use binomial. You could use normal approximation to solve this. And it's just the same thing you have known. Just a little addition will be done here. It's very simple and very straightforward. So what do you have to do? If you remember the process I highlighted some minutes back, I told you that the first thing is for you to check if the normal distribution is appropriate in this scenario. And to check, you have to go on to find for the mean multiplied by P, and then you go for the mean multiplied by Q. These are the two, and both of them must be greater than or equals to 5, greater than or equals to 5. I told you already that some people make use of greater than or equals to 10. Sometimes you may see in a textbook, some people may make use of 10 in these cases, but we'll be using 5, all right? Now, if you go on to do that, of course, for you to find your mean, you have to find your mean first. So your mu, which I believe you all know for a binomial distribution, is n times p. And we have our n as 75 and p as 0.6. All right. So if you press that on a calculator, I'm sure you know you're going to get a value of 45. So you have 45 right there. Now, let's do this check quickly. Our mean 45 multiplied by p, 0.6. And then also we have 45, our mean, multiplied by our q. Of course, you can recollect that p plus q must be equals to 1. This means our q in this case is 1 minus p, which is 1 minus 0.6, which is 0.4. All right, so our q here will be 0.4, so that will be 45 times 0.4. So we go on to solve these two things. You would have the value of, what can you give me your answer quickly? Press this on the calculator. What is 45 times 0.6 and 45 times 0.4? Of course, 45 times 0.6 is 27, and 45 times 0.4 is 18. All right. So if you can look at this now, you can see that the criteria for it being greater than equals or equals to 5 is met already. So we can check that, and we know this is done. All right. So the next thing now is for us to go on now to find our mean and standard deviation. Now we have found our mean to be 45 already. Our standard deviation, obviously, if you recollect, for variance of a binomial distribution, we have NPQ. Whereas, of course, the standard deviation will be the square root of variance. In this case, now we have our n being 75, our p being 0.6, and our q will obviously be 0.4. So let's see, what does this give you? If you press this on a calculator, this will be square root of 18. All right. Now, if you look at what's going on here, we're done with the first two steps. The third step was for us to write in probability notation. Luckily for us, in this question, we have it already written in probability notation. So you can see right here, we have it written already. So that step is perfected, all right? Now, the next thing for us, which is the most vital part of this whole thing, is what we call the test for continuity. Test for continuity. I'm going to give you a detailed explanation on this because I want you to be very strong in this aspect. This is the key part of you being able to always solve these questions without any stress, seamless solving. Of course, everything I've said here, I believe everybody really follows this. This is very simple. Check if it's appropriate for a normal approximation and go on to find the mean and standard deviation. Everybody can do that. And then you go on to write in probability notation. Now, the major one, which is what you want to really learn this night, is the test for continuity. All right, now I'm going to decide to solve this without test for continuity. Then you're going to understand, that will give you a much better understanding to understand why we're going to always have to make use of what we call continuity correction. Sometimes you see it being said as test for continuity. Some other people may say continuity correction. It's more like a correction factor that helps you improve your result and gives you a much more better approximation of the correct answer. So we're going to see how it works. Now, I'm going to decide I want to act like I don't know about continuity correction. So I'm going to solve without continuity correction. You're going to see the answer we're going to get. And we're going to solve using continuity correction. You're going to see the answer we get. Now, if we're going to solve without continuity correction, let's do it right now. We have, of course, this step number 3, we're going to write in probability notation. So this is what we have right here. Now, don't forget, we're trying to use normal distribution to solve binomial distribution. We have this under binomial. We want to use normal. All you have to do is to just do what we do when we see a question like this in normal. If you have a question like this under normal division, one of the things I told you guys, and I've spent so much time explaining this, is that you don't have a table that can solve a question like this. And that's the reason why we do something, which I've emphasized on it so well. We do what we call standardization. So you have to standardize because we make use of a standard normal curve to solve the questions like this. So in the process of standardizing, you know that already. You want to have standardization is just simple. You convert, you get your z, which is x minus mu over sigma. Of course, you can know the reason why we went on to find mu and sigma. It's actually because of this process. All right, because we needed it for standardization. So if you look at what we have here, we have x. So we want to standardize this. We have our x minus mu over sigma. Let me make this bracket a bit more bigger. Greater than or equals to 52 minus our mean was 45. And our sigma was square root of 18. All right. And if you go on to solve this, probability of this will turn to z, obviously. And we have greater than or equals to 1.645. All right. So I'm sure you know what we're supposed to do next in this case. This is the moment where you make use of your table. You make use of your table. So guys, let me see how excellent you can be. Can somebody quickly solve this question? I would obviously also solve it. But can you solve this question using a table? What's going to be your answer? What's going to be the answer when you're solving this using a table? So keep on solving so that we can, of course, you can get more stronger and better in solving questions like this. Now, we go on to draw our symmetric curve. Of course, you know that I told you it's symmetric about the mean. And for a standard normal distribution, Z, it has a mean of 0 and a standard deviation of 1. So obviously we have 0 right here. It's symmetric about the mean. And we're looking for 1.645. I told you the process to doing this is just go on to try to find where do you feel 1.645 is going to be. If you look at what we have here, 1.645, I can put it somewhere here. Of course, I'm not drawing this to scale as I explained already. So let's put 1.645 here. Told you the next thing to do is just roll this up, right? Then check up your sign. This is greater than or equals to 1.645. Greater than obviously will be talking about this place. So this is the point of interest. All right, this is the point of interest. So can you guys go on now to give me an answer? Of course, just give me an answer. Let me get, what's your table answer when you solve this? Okay, many of you, I can see 0.495, somebody says 0.443. All right, for you to check this, of course, you want to go to your table and you want to be looking for 1.6. You want to look for 1.6 under 0.04. All right. Now, whatever answer you got will be, as I told you already, will be for this area. All right. But don't forget, this is the area of interest. So whatever answer you got here, you have to make use of 1 minus the answer you got here. Because I told you already that your tables don't give you answer from right to left. Rather, you get your answers from left to right. Okay, so anybody with an answer for 1.645 using your table, 1.6 under 0.05, 0.9505. So you would see this is going to give you an area of 0.9505. So obviously, for you to get this other space, you want to do 1 minus 0.9505, which will give you 0.0495. Now, obviously, that means the meaning of this is that the value for my probability of z greater than or equals to 1.645 is equals to 0.0495. All right. Now, pay attention to what just happened right here. This means we have gotten our answer for probability of x greater than or equals to 52 to be 0.0495, making use of the normal distribution. But here's the problem. If you make use of a program, now we have lots of packages, tools that can give us this answer without having to manually solve. You make use of a program or any software to solve this. The result this gave us is 0.0611. This is the result it gave us as the answer. And right here, making use of the normal approximation without the test for continuity, without the continuity correction, we're getting 0.0495. If you look at these two answers, 0.06, 0.04, pretty close, but not that close. So obviously you can see that if you wrote this as your answer in an exam, whereas this was the answer, I'm sure you know that you would not be correct because it's still a bit further. And the reason for this level of disparity is because we did not include the correction continuity. The continuity for the correction for continuity, whatever, however we want to say it. So you see, that's the reason why I will be introducing to you now the way to solve tests for continuity. Now, what you have to do is very simple, and you don't need to feel it's a big deal at all. So instead of us solving this way, when we had probability of x greater than or equals to 52, what we would have done using test for correction continuity or correction continuity would have been for us to, rather than using 52 here, we would have used x greater than or equals to 51.5. Now, this is why. You see, if you were told to, you are trying to get all of 52, the question said it's not just greater than 52. There's a difference between greater than or equals to 52, and there's a difference between greater than 52. This one included 52. In order to ensure that we cover up all the areas from 52 upward, we would be taking it, we're moving to the right in this case because it's greater than 52. So we would be, instead of starting all from here, we would be coming just a bit backwards to pick all the areas. In this case now, we will be very strongly including 52. Now, that's the reason why we're going to be using 51.5 rather than 52. Now, let me move just immediately to answer probably a question on the mind of some of you. What if we had x greater than 52 alone? That means in this case now, we are not including 52. In this case, I don't want to include any of 52 because you can see, well, what is being said here? We are not including 52. It said greater than 52. So in this case now, what we will be doing, we would have the probability of x. What do you feel is going to be the answer? We're not going to be using 52 in our calculation. We're going to be using 52.5. So in this way now, you can see that we are not including any of 52 in this case. We are excluding 52. So we are starting from 52.5. So 52 is not going to be featured in this calculation now. That's what we call continuity correction. So let me give you another instance. What if we're dealing with probability of x less than or equals to 52? What do you feel would be the answer in this case? Now, we are told that 52 less than 52, but also equals to 52. So obviously, you can see that we want to include 52 in this case, but now we are sweeping to the left because this is less than. So we're sweeping to the left. So we don't want to start from exactly 52. We want to start a bit before that 52. If you understand what I'm saying, if this was 52 now, and we are asked to talk about less than or equals to, now if this line was 52, we want to take it a bit backwards so that we can cover the entirety of 52 and everything in this band. So in this case now, we'll be having x less than or equals to 51.5. You can see we have taken it a bit backwards. Now, another scenario which is possible for you to have is what if we have x just less than 52? Now, in this case, you can see we are not including 52. We are not including 52. So if this was 52, if this line represented 52, and we want less than 52, obviously we are moving to the left in that case. And we don't want to include 52 because this doesn't include 52. This said less than 52. So we want to exclude 52. So in this case now, if it's just less than 52, you know that if this was, look at it, just look at the number line. If we had 52 here, of course, we have, let's say 51 here. We have 53 here. In between, we have 52.5, we have 51.5. So if we're saying less than 52, we're not including 52. Obviously, we don't want to include 52, so we'll be starting from 51.5. So in this case now, when it's less than 52, we want to say probability of, oh, sorry, I think I made a mistake here. When I said, sorry, this is wrong. What I did in this third one is actually wrong. I'm trying to include all of 52. So this should be 52.5. Sorry, it's more like, let's use this number line in this case. If we're trying to cover from 52 to the left, of course, you want to include all of 52. So you want to move it a bit backwards. And in that case, you'll be having 52.5. This is 52.5, not 51.5. Sorry about that. So we're dealing with 52 now, and we don't want to include 52. So we don't want to start from 52 because the inequality said just less than 52. We want to start from 51.5 in that case. So if you see what is going to happen here, we'll be having probability of x less than 51.5. All right, this is what we call test for continuity. If you have a question, shoot it quickly in the comment section. Let me have you quickly. Okay, I think somebody has answered the person's question already. All right. Okay, that was a question. The question that came was a question based on the previous solution we did. So if you let me just do a quick recap on this. This is the most vital part of this thing we are solving. This is the most vital part because every other thing we have talked about is something you are all familiar with. Now, without doing test for continuity, this was the normal answer we're supposed to get. If you use a program or whatever, you get this answer for this question we're giving. Now, we want to use our calculations to do it using normal division. We don't want to stress all the, I told you already, this is going to be very stressful. You have to use binomial to solve from 52 to 75. So you don't want to go through that process. You want to make use of normal distribution. Now, if you just fix this under a normal distribution, of course, if x is greater than or equal to 52, you want to standardize this, and then you got 1.645. You find the probability to be 0.0495. But looking at what we have here, the disparity is quite large. So we don't want to fix our answer on this. So we have to go on to do the correction for continuity. All right. Now, trying to understand the correction for continuity is just very simple. If you have this number line, I'm going to use, of course, in the next question again, I would still try to explain the correction for continuity. We don't want to, if we have 52 greater than or equal. Now, let me tell you one thing. Under correction for continuity, all these signs matter a lot. This is what will determine what you're going to be doing. So if you have greater than or equals to 52, greater than or equals to 52, you see, in this case now, you can see clearly that we're dealing with all of 52, 52 included. Now, if this was 52, if we went on to start from here, we don't feel very convenient in doing that because we are to include 52. The area from here may not touch the 52. So we move it a bit. Since, look at the, okay, no, we can't, the sign said greater than, so we're interested in all of this space. So move it backward a bit. We're starting from here. So we're starting from 51.5 when we are dealing with a case like greater than or equal to 52. If we're dealing with just 52, now just 52, that means we're not interested in 52. Just greater than 52. We're not interested in 52. So we don't want 52 to be included in our calculations. So we'll move it a bit forward since 52 is not very important and we'll be having 52.5. Now, when we're dealing with less than or equals to 52, less than or equals to 52 is included. Less than, we're moving to the left in that case. So we want to shift it a bit backwards. Of course, backwards in this case now, we'll be using 52.5. So we can, in this case now, we'll be covering all of it, including 52. For that of just less than 52, now 52 not included. 52 is not included. We want to find all the left-hand area from 52 downwards without including 52. In that case now, we don't want to start from 52. We want to start after 52. That will be 51.5. So that in this case now, whatever we get now will not be including 52. This is how you test for continuity. And you would never go wrong if you follow this very simple process. Now, there's a very vital question I expect to be on your mind. If you are having, what if, the question is, what if you have to just solve for equals to 52? That's a very important question. Probability of x equals to 52. How do we solve this? Because we have done for every other one except equals to 52. Well, in this case, what you do is that you would subtract. This is how you're going to solve this. Of course, you'll be finding x less than. Now look at what you're going to do. You're going to subtract 1.5. So if you're having 51.5, then you'll be having 52.5. In this case now, you see that the area you are talking about now will cover all of it, will touch 52 properly. Between 51.5 to 52.5, is where you're going to be using. So this is what you're going to be solving. If you have equals to 52 as a question, of course, using your test for continuity, this is what you're going to be doing. So you will not go on to say you want to just solve directly. No, you have to do this. Of course, this is appropriate for normal, because this question cannot even be solved using normal distribution, because there is no area right here. So this is where you're going to be able to touch the area that would now include that of 52. So when you have a question like this equals to anything, you would subtract 0.5 from the value to the left, add 0.5 to the right. This is what you will now be solving using your normal division. So let's quickly move on to now the question we were solving before, that we got 0.0495. Let's try and now apply our test for continuity. Of course, and we're not going to do so much changes. Of course, you have seen the answer. What we want to just do is, we're still going to follow the same process of standardization. But in this case now, the difference is that we're not going to be using 52 now again. We're going to be using what? 51.5. We want to use 51.5 now. That's just the difference between test for continuity and not testing for continuity. So in this case now, when we have 52 greater than or equals to 52, we're using 51.5. So if you go on to solve this now, you can go on to solve this. When we use 51.5, you'll be getting 1.532. So can you go on now to solve this using your table again? Can you go on to solve this? Of course, if you want to draw your table, your curve, of course, symmetric about 0, the mean, then you want to have 1.532. Now you're talking about greater than or equals to, greater than or equals to. So obviously you are interested in this side. So can you give me the answer for this using your table quickly? Give me the answer for this using your table. Give me the answer for this using your table quickly. Anybody? Very quickly. I want you guys to get much stronger in using your table to solve. All right. Anybody with an answer yet? What's the value of this area? What do you get as the value of this area? Of course, I told you guys already. Of course, you want to be looking for 1.5 under 3, 0.03 on your Z table. And that will be giving you the area for this portion. All right. Whatever you find, it doesn't give you value from right to left. Okay. Somebody got the value as 0.063. Of course, that's very correct. 0.063. Now, can you see that when we applied testing for continuity, we got 0.063. Now, note the difference now. The use of test for continuity gave us this beautiful answer. Look at the correct answer normally when using a program or whatever, you got 0.061. Are you seeing clearly that the values now using test for continuity has given you a much more better answer with fewer disparity, a smaller disparity? So this is the advantage of using test for continuity. Now let me give you a summary of this quickly. Solving this question, the one we have right now, if you decided to solve without testing for continuity, without correction continuity. So we look at two different questions: probability of x greater than or equals to 52 and probability of x greater than 52. So if you don't use correction continuity. That means no correction continuity. The value you got for this, which we just solved, was 0. I'm sure you recollect this. We just got this answer. And of course, I'm sure you know that that value will be the same for this question also, for this particular greater than 52, because I'm sure you understand why. It's not going to make a difference if you're using equals or not. If you use the same 52 without correction continuity, your values are going to be the same thing. I'm sure you understand that. So it's just that way, because 52, if you use 52 here for when it was greater than or equals to, and you don't use 50, and you use 52 when it was just greater than, your values will be the same. That would have been the same 0.0495. Now, if you decide to use correction continuity, that means you decided to apply the rule for correction continuity. In this case now, instead of using 52, now you're using 51.5. And in this other case, instead of using 52, you're using 52.5. Now, what are you going to get? You're going to get 0.063. And for this other one, you'll be getting 0.0385. We did not do this, but you can go on to confirm that using correction continuity, you would get this value. Now, what's the exact value when you're using, if you're able to solve this using a binomial, either you solved with your hand or using a computer program, what's going to be the exact value? I told you guys already that of this was going to be 0.0611, and whereas this will be 0.0367. So can you see the importance of correction for continuity? You can see how close the correction for continuity answer it is to the exact one, and how close it is for this one. And look at the disparity when you decided not to use correction for continuity. So this is basically how you use normal distribution to binomial distribution. So let's solve one question very quickly, then I'll give you an assignment. That will be all for this class. It's a very simple one. All right, so the question is for you to use normal approximation. So use normal approximation to calculate the probability of x greater than or equals to 17. Of course, we are given n equals to 30 and p is equals to 0.50. All right, so you can start to solve that with everything I've explained. Of course, I will keep solving right here. Okay, I can take this off. Now, looking at what we have here, the first thing to do is for us to go on to check. I'm sure you know step 1 is for you to, and this must be greater than or equals to 5. So your mean here, obviously, your mean is equals to n times p. In this case, your n is 30 and your p is 0.5. Of course, your mean will be 15. All right. Now, if you have your mean to be 15, that's nice. So let's go on now to test this. That'll be 15 times 0.5. What do you get there? You obviously will get a value. If you go on it, it's obvious you will be getting a value greater than 5. And that was 7.5. This gave you 7.5. Of course, that means we have, this is checked. The first is checked. And for mu times q, of course, in this case now, your q is 1 minus p. 1 minus 0.5 will still be 0.5. So your mu times q will also be the same thing we are writing here. So this is confirmed. So we can make use of the normal approximation. Of course, the step 2 is for you to go on to find the mean and standard deviation. We already have the mean to be 15, but our standard deviation obviously will be the square root of npq. That will also be the square root of what our n, 30 times p, 0.5 times 0.5. If you do this, that will be square root of 7.5. Is this 7.5 square root of? Yep, square root of 7.5. And then we have that to be 2.739. Okay, good. So we have found our mean and our standard deviation. Step 2, perfected. Now, step 3 is for you to go on to write in probability notation. Of course, in this question, you were given it in that format already. So you don't need to sweat over step 3 because that was already given. But in the case where you were given a word problem, you will have to write it appropriately. All right. Now, looking at this question now, just let me, if you're going to, I'm not going to use without correction for continuity in this case because I already told you the importance of testing for continuity and you already understand that. So let's just go on to test for continuity to have the correction for continuity being done. So look at what we have right here, greater than or equal to 17. Just to give you a little more explanation on this, let me just, if you're going to draw this using, if you're going to graph this using your binomial distribution, let's say, of course, let's say this was 15. Let's say this was 16. Let's say this was 17. Let's say this was 18. So the way the graph for binomial distribution is always is something of this form. Let's say we had something like this. Something like this. Let's just imagine we had, so this is how the graph for binomial, we don't normally have the bar on the point. So this is, you can notice 15 is here, 14 point, the bar starts from 14.5 to 15.5 to accommodate for 15, whereas for 16 it was from 15.5 to 16.5. So just similar to what I explained earlier, look at what's going on here. If you were told to find the probability of x greater than or equal to 17, you went on to now say, oh, with, like, I'm just trying to buttress the importance of testing for continuity. You went on to now say, I want to just start from exactly, I'm trying to find for greater than or equal to 17. I want to start from exactly 17, and I want to find, of course, you know, area. When we are finding probability, we are looking for area. So if you want to just start from 17 without, you just want to start from 17, that means this is the area you'll be dealing with. And you can see that you are not including the bar, the other, you are excluding a whole half of the bar for 17. And that's the reason why you notice in our previous question, the answer we got when we did not do the correction for continuity wasn't very nice, because this is what you'll be doing. You will be eliminating a good portion of the area you're supposed to have. So that's why we have to test for continuity. Another way to see this is, if you had to, let me draw the little curve right here that produced this. If we had, of course, the mean, I'm sure this is an x normal distribution. I'm not standardizing yet. Because the mean is 15, so this is 15. 17 will be somewhere here. Now, with greater than or equal to 17, now we're interested in all these portions. Now let's just use another analogy. If you wanted to sweep an area, of course, you don't want to put your broom exactly on that. If you want to sweep everything from 17 upward, you want to put your broom a bit after before 17, so you can easily pack up everything in that specific area. Just if you can use that understanding to understand the reason why when we test for continuity and we are talking about including 17, you want to use, instead of using just starting from 17, you want to use 16.5. So what you're going to be doing here is to say this probability of x greater than or equals to, you'll be using 16.5 in this case. So in this, using this one now gives me the ability to factor in every part of 17. All right. So this is the reason why you do the correction for continuity. All right, so let's go on to just apply that. And now you have this. Of course, you know that I told you already, you don't have a standard, you don't have a normal distribution that is normal distribution table. You have a standard normal distribution table. So you have to go on to get this standardized, and that will be by you having this done. Don't forget, now we're using 16.5. Our mean is 15. Our sigma was 2.739. So we will be having probability of z greater than or equals to what? 0.55. So it's always good practice for you to have your diagram drawn. We're having 0 here. We have 0.55, right? We have 0.55 right here. So what you have to do is to draw up that. What space are you interested in? Greater than or equal to, so we're interested in this space. All right. So you have to go find this on a table. And what do you get as your answer? Can anybody give me an answer? This is something I think you should be able to do by now. Of course, you want to go on to find your table. What's your answer? Don't forget, I'm interested in this portion. So, and don't forget, I've said this so many times, you don't get your values from the table from right to left. It gives you from left to right. So whatever, if you find this on the table, whatever you answer you're getting will be mirroring this place. This is where you'll be getting from the table. And for you to find this, you will have to make use of 1 minus that. Of course, what's your answer? Anybody here with an answer? So we have 0.55. That will be 0.5 under 0.05. That will be 0.7088. So, and of course, the portion right here, as I said, that comes from the table is 0.7088. So you have to go on to subtract that from 1. And you will see that the value you'll be getting was 0.2912. So this is the answer for this question, making use of the normal approximation to solve a binomial distribution question. So that's how simple it is. Very simple and straightforward. So take this assignment down, and I really hope you get the solution very quickly. It's very simple, just a question. All right, so the question is, if a baseball player if a baseball player's batting average is 0.32. So the question is for you to find the probability that the player will get at most 26 hits in 100 times at bat. So right here is the question I want you to try and solve. If a baseball player, okay, it looks like camera, all right. So if a baseball player's batting average is 0.32, find the probability that the player will get at most 26 hits in 100 times at bat. Then I want you to find the probability that the player will get exactly, so question number B, exactly 26 hits. All right, so that's the question I would love you to solve to strengthen your knowledge on this. So that's where we're going to stop, guys. I really believe you have been able to understand this topic. It's that simple. That is all about it. There's nothing more, nothing less. All you have to do is to understand majorly how to use the correction for continuity. That's the major key to making use of normal approximation to binomial distribution. Thank you guys for joining. I wish you all the best. Enjoy.